In this module, you will learn about different types of relations and their properties. Let's take a quick look at relations that you learned in your previous class. A relation R from a non-empty set A to another non-empty set B is a subset of the Cartesian product of A and B. The subset R is derived by describing a relationship between the first element and the second element of the ordered pairs in A cross B. Let us see an example to make our concept stronger. Here, we have to find a relation R from A to B such that for any A in A and B in B, A is a factor of B and also A is less than B. That is, in the given sets A and B, we have to find the set of ordered pairs A, B such that A is a factor of B and A is less than B. Let 2 and 4 be any arbitrary elements of sets A and B, respectively. Now, 2 is a factor of 4 and also 2 is less than 4. So, 2, 4 is one such ordered pair that satisfies relation R. Likewise, other such ordered pairs can be obtained. Thus, the set of all the ordered pairs so formed is the relation R, which is as shown. The set of all the first elements of the ordered pairs in a relation R from a set A to a set B is called the domain of the relation R, and the set of all the second elements of the ordered pairs is called the range of R. If the ordered pair A, B belongs to set R, then we say that A is related to B, which is denoted by ARB. You also learned that if the number of elements in set A is P, and the number of elements in set B is Q, then the total number of elements in the Cartesian product of A and B is PQ, and the total number of possible relations from set A to set B is 2 raised to the power of PQ. Different types of relations. Consider set A with elements 1, 2, 3 and 4. The Cartesian product of A with itself consists of 16 ordered pairs, as shown here. Let us define a relation R on A, defined as the set of all ordered pairs x, y, such that x plus y is equal to 15. Recall that any relation R in A is a subset of A cross A. In this case, no ordered pair satisfies the condition that the sum of their elements is 15. Hence, relation R has no ordered pairs in it. These types of relations are known as empty relations. Mathematically, a relation R in a set A is called an empty relation if no element of A is related to any element of A. That is, R is an empty set and is a subset of A cross A. Proceeding further, let us define a relation R in A as the set of ordered pairs x, y, such that x plus y is less than or equal to 8. Choose any arbitrary ordered pair from A cross A. Observe that the sum of its elements is less than or equal to 8. Here, all the ordered pairs satisfy the condition that the sum of their elements is less than or equal to 8. Hence, we get a relation R that has all the ordered pairs present in A cross A. This type of a relation is known as the universal relation or total relation. Mathematically, a relation R in a set A is called a universal relation or total relation if every element of A is related to every element of A. That is, R is equal to A cross A. An empty relation and the universal relation are sometimes called trivial relations. There are 4 different types of relations. Let's first see when a relation is said to be reflexive. Let T be the set of all triangles in a plane. Define the relation R in T by the set of ordered pairs T1, T2 such that T1 is similar to T2. If an ordered pair T1, T1 is in set R, then it implies that T1 is similar to itself, which is true, since every triangle is similar to itself. And this holds true for all the triangles in set T. Hence, we can say that every element of set R is related to itself. Such types of relations are called reflexive relations. Mathematically, a relation R in T is said to be reflexive if every element of set R is related to itself. That is, the ordered pair x, x belongs to R for every x in T. Next, let's see when a relation is said to be symmetric. Again, consider the same relation R in T defined by T1, T2 such that T1 is similar to T2. Let T1, T2 be an ordered pair in set R. Then it will imply that T1 is similar to T2. So we can also say T2 is also similar to T1. This implies the ordered pair T2, T1 is also in R. Such relations are called symmetric relations. Mathematically, a relation R in a set T is said to be symmetric if ordered pair x, y belongs to R, implies that ordered pair y, x is also in R for all x and y in T. Let us take one contradictory example. Relation R in the set 1, 2, 3 is not symmetric. This is because the ordered pair 1, 3 belongs to R, but 3, 1 doesn't. Note that it is wrong to say that it is sometimes symmetric or is symmetric as far as 1 and 2 are concerned, since being symmetric is a property of the whole relation. Let us now move on to transitive relations. A relation R in T is said to be transitive if x, y and y, z belongs to R, implies that ordered pair x, z also belongs to set R. Let's check the transitivity of the relation R in T, which is defined by the set of ordered pairs T1, T2, such that T1 is similar to T2. Consider the ordered pairs T1, T2 and T2, T3 in set R. By definition, T1 is similar to T2 and T2 is similar to T3. Now, T2 is similar to both T1 and T3, so this implies that T1 is similar to T3. This in turn implies that the ordered pair T1, T3 belong to set R. Hence, ordered pairs T1, T2 and T2, T3 belong to set R, implies that T1, T3 is also in R. This shows that the relation R in T is transitive. Now, let's come back to relation R in set T. We observed that the relation R in T is reflexive, symmetric and transitive. Such a relation R in T is called an equivalence relation.